Okay, so you see, in the last class we considered the classical gas, right? And then after that we discussed the concept of mean molecular weight. After that we also discussed the various applications of both these concepts for our sun and solar evolution and all that. So this was what we covered in the last class. Again, I think as one of you students pointed out, regarding equation 38 there will be a correction, and that will be that instead of x, so it will be just x. Okay, so the correction will be x, we will be putting x square, right? কি হবে এটা বলো? So it will be, just a second, so the substitution will be, this is equal to p square by twice m kt kbt. Okay, with this, now let us today talk about Fermi-Dirac statistics. Okay, so previously we talked about classical gas. So the next very important thing is what when during the stellar evolution, during the course of evolution, it can happen that the gravity slowly becomes the dominating factor, then there is a collapse and atoms come close to each other, and as a result of that there is a ionization due to pressure, sort of pressure ionization. And at that time what happens, all the atoms, they get ionized, and then electrons become free and atoms becomes, so they are separated, electrons get separated from atoms. And at that time inside the entire star, okay, so previously inside the entire star we can consider of like there is a sort of electron gas. I'm just giving you a picture, and then there is similar ions, all that. Also there are a huge quantity of photons as well, but now among these three something very drastic is going to happen. What is going to happen is that previously ions and electrons were in the classical regime, they were following the same EOS, but under the changed circumstances, when the density becomes high, then even ions, they follow the same EOS, but the EOS of the electrons, they change. What I mean to say is that the pressure, which was basically dependent on rho, T and composition, this is the general form. In this scenario, when the density increases, all of a sudden the temperature dependence vanishes, and this has got drastic consequences on the stellar evolution. So this is what we are going to discuss today. Okay, fine. Now we have already discussed that stars radiate and therefore they lose energy. So as a result of this, the core of the stars usually contract and the central density increases over time. Now when the density becomes high enough, as I was saying, the classical behavior for electrons, they first break down. This is important. So as your density increases, it is in fact the electrons for whom the equation of state changes first. Now you might be thinking, what about the ions? Do the EOS change for them? I will talk about it later on. In fact, it changes, but for neutrons, and this is important for the neutron star. Okay, so as I was saying, when the density becomes high enough, the classical behavior for the electrons, they change first, right? Now to really see how this happens, it is important to examine how the central density and the critical density. They scale with radius as the star contracts. Now, from dimensional analysis, you see the central density. What should it scale to? Well, it is just equal to m by r cube. So, it is basically scaling is like this, where of course m is the total mass and r is the stellar radius of the star. Now, to estimate the critical density, so this was central density. To estimate the critical density, you see, we need an estimate of the central temperature. So, what about the central temperature? Now, let us try to estimate it. Well, you might have seen this thing previously. Remember when I was talking about the equation of hydrostatic equilibrium? There we discussed the same thing. So let me just recapitulate. So let us start with the equation of hydrostatic equilibrium. So this means dpdr. Just a second. Let me give this equation a name. So this is following our class lectures. So this is equation 65. And so the equation of hydrostatic equilibrium is basically this into rho r 66. Now let us adopt the approximation that rho is approximately equal to rho c rho average, and this is approximately m by r cube. Then from again dimensional analysis, what will we have? You see, we will have Pc by R. This equation I am talking about this. So basically I am talking about this. Using these two approximations, this equation now becomes Pc by R is approximately equal to Gm by R square into rho, again approximately equal to Gm by R square into m by r cube, right? So this is G m square by r to the power 5. So this means that we can write Pc as, so from the previous page, so we can write Pc as G m square by r to the power 4. This is equation 67. Now, if our central gas, basically it follows ideal gas law, then what happens? Then you see we can write Pc is equal to rho c Kb Tc divided by mu into mass of proton. So this is basically equal to m by r cube Kb Tc divided by mu into mp, equation 68. So from this equation and also from here, these two, we get Tc is approximately equal to G m mu mp divided by Kb into R. So this means Tc is proportional to 1 by R. Okay, 69. So the critical number density now NQ, right? So this is equal to, just a second, 2 pi me Kb Tc divided by h square to the power 3 by 2, and this is proportional to, you can see, Tc to the power 3 by 2, or this is proportional to R to the power minus 3 by 2. Okay, so we get the critical number density scaling relation. But previously we already observed, you see, from equation 65, the scaling for central density is R to the power minus 3, whereas the scaling for the critical number density is R to the power minus 3 by 2. So what does this mean? This means that, you see, so let me again write down, the physical central density is proportional to R to the power minus 3. So this means that as the star contracts, the central density rises faster than the critical density required for quantum behavior. Okay. It is important to note also that the critical number density for proton degeneracy is higher. Proton degeneracy, it is higher by a factor of mp by me to the power 3 by 2. As a result, the electrons will first become degenerate. In addition, if the density is high enough, the electrons can become relativistic as well. Again, recap what I have just said. So basically, you see, critical number density, it scales as R to the power minus 3 by 2, whereas the physical number density scales as R to the power minus 3. So this means that as your star contracts, the central density, which means this, right, Nc, here you see the critical number density is this, and this is your just physical number density. So the, just a second, central density, this one, you see, power is minus 3 and this one is minus 3 by 2. So this one basically it rises faster than the critical density required for quantum behavior, right? So this is what I was saying till now. So now let us start with the case for T is equal to 0 degenerate electron gas. Well, so what we will be doing is we will be considering the case when n is much greater than nq. Now this condition means that the temperature, it will satisfy this relation. Let me write it down. The relation is basically, we have already talked about this previously, so I am just skipping the old part, I am writing it down. So this means that this is the requirement, that the temperature must satisfy. I am writing this relation in terms of the temperature, and this is equation 71. Now you see, if the temperature is much lower than the critical temperature, then the gas can be regarded as cold. So we will have a cold gas, cold Fermi gas. Okay. Now what we are going to do is we are going to idealize this cold gas as having T is equal to 0. Okay, so this is what we are going to do. Regarding the finite temperature Fermi gas, we will talk about it later on. Okay, now you see this cold gas of electrons, so basically T is equal to 0, cold gas. This is an idealization, it is important. So T is equal to 0, cold gas of electrons. So this is what we are going to talk about. There also called degenerate. Now why? The reason is that electrons, in this case when t is equal to 0, what happens is that electrons, they have fallen into the lowest quantum energy states, right? T is equal to 0. What can be lower than this in terms of temperature? And as we know that electrons, they are what? Fermions, right? So when they have fallen into the lowest energy state, this means that they will always be obeying the Pauli's exclusion principle. But this time, if they are in the lowest quantum state, according to the Pauli's, so as they will be obeying the Pauli's exclusion principle, so they must be distributed such that the energy levels up to a certain level is completely filled. Otherwise, Pauli's principle will be violated. If all of them are in the ground state, then Pauli's principle is going to be violated. Pauli's principle, right? So what is going to happen is that slowly and gradually they will be filling up to a certain level. So this is what I am saying, that as a result of obeying the Pauli's principle, they will be distributed such that the energy levels up to a certain level is completely filled. Now the highest energy level here that is filled, okay, the highest energy level is known as the Fermi level, EF, and it has the corresponding momentum known as Fermi momentum, known as PF. Okay. Now let us write this down. So from relativity we have EF is equal to E square is equal to P square C square plus ME square C to the power 4. So this is relation 72. Of course, where ME is the rest mass of the electron. Now we will write down the occupation number. So as I am saying that all the levels are filled up to EF, so the occupation number is the simplest possible. So this is the simplest possible occupation number. So this is equal to 1 if energy is less than equal to EF, and this is equal to 0 if energy is greater than EF. Okay, now, or this is occupation in terms of energy, and in terms of momentum, the same occupation number we can write it down as again 1, 0. It is equal to 1 when P is less than equal to PF, and it is 0 if P is greater than PF. Okay, but remember that this entire thing, okay, is happening for T is equal to 0 case, right? So can anyone tell me what happens if this is not T is equal to 0? So if this is not equal to T is equal to 0, say at some finite temperature, say T is equal to 300 Kelvin, what will happen? Or say T is equal to 3000 Kelvin, what will happen? What will happen? Yes, this the things will be same. Okay, the Fe, it will not be like this, as you can see. So here Fe, it is not equal to 0 anymore. Again this is, so it will be greater than 0, and this time it will be less than 1. Okay, the behavior will be like this. And what number will it be? It will depend on the Fermi-Dirac statistics. So as you can see, finite temperature case is very much difficult, right? But we will do this in a separate class, not today. This is very interesting. Okay, so let me come back to what I was talking previously. So we will be talking about the T is equal to 0 case here. Okay, now you see for electrons, just a second, it will be black color. Yeah, for electrons we have Gs is equal to 2, so that the number density of electrons we can write down as, you see, this relation here. This is equation 73. Now, this relation provides a direct link between the number density of electrons and the Fermi momentum. Here you see there is a direct link between the two of them. Now, the density of the gas is related to Ne by equation 54. So let me just write it down again. Here, density of the gas. So this is again related to Ne like this here, and so we have this relation, equation 74. Note that mu E is equal to twice by 1 plus x, and this is the mean molecular weight per electron for a fully ionized gas. Of course, x is the mass fraction for hydrogen. Now, you see this previous relation, this one, we can in fact rewrite this equation. So, let us rewrite this equation. Okay. So, upon rewriting, so basically we will have rho is equal to rho 0 mu E into xf whole cube, or x. Sometimes it is written as x, sometimes as xf cube, xf. Anyway, so this is equation 75, where rho 0 is a constant having the dimension of density, okay, and it is basically, it has the value 8 pi by 3 me c by h whole cube into mp, and the value is 0.98 into 10 to the power 9 kg per meter cube. So this is equation 76. And here, as I was saying, xf is just equal to pf divided by me into c. Okay, so now with all these things, we are ready to write the relation for pressure. So we are now ready to use the pressure integral. Okay, of course, taking into account the occupation number. So I am just writing down the expression for the pressure integral, and look at it. How does it look? You see, so this is the pressure integral, and of course after taking into account, you see it is just 0 to pf. Why? Because afterwards the value is just 0, right? So this is the relation we are getting, okay, for the pressure. And again, this relation, it can be again rewritten as, for better understanding, we can rewrite this as this relation. So you see, I am just taking the constant terms outside, and again I am redefining this in terms of x, okay, where you see x is equal to p by mec, and as I was saying before, xf is equal to just, it will be pf by mec. What about the constant b? Well, the constant b, let me again write this down here, okay. So this is the value of the constant b, as you can see, and this is equation 79, this is equation 78. Okay, now it is important to note that just like here we have used the pressure integral and obtained this relation, similarly for the kinetic energy density. So This is for pressure, electron pressure. Okay. Similarly, for the electron kinetic energy density, we can have this relation. Here. See, so this is the basic relation. Again, 0 to PF limit. This is equation 80. And again, taking the constants out, this equation can be rewritten in this form. Here. Okay, equation 81. So, we are now going to concentrate on this equation over here and this equation. Fine. So, we are going to concentrate on this equation. But it is important to note that basically equation 81 over here, then equation 78, and also this equation, equation 75. These three equations, basically, they complete the equations of state for a completely degenerate gas in parametric form. Okay, so let me write down. So basically, this rho equation, P equation, okay, and what was the last equation? U equation. They basically complete the EOS. So together they will be called as EOS for a completely degenerate gas in parametric form. And remember, all these things for T is equal to 0. For T not equal to 0, they will be very much different. Okay. Now, these equations can be integrated analytically. Okay. And this is what I am going to do next. So, for the sake of convenience, let me again write down these equations. Okay. So, basically we have, you see, rho is equal to rho 0 mu e xf cube, right? Next we have Pe equal to b 0 to xf x to the power 4 dx divided by 1 plus x square. Right. After that, we have kinetic energy density UE is equal to thrice of U0 into again 0 to xf, and this is x to the power 4 dx divided by 1 plus square root of 1 plus x square. Now this was equation 75, this is 78, and this was 81. What are these two constants, b and u0? Well, b is equal to 8 pi by 3 MEC by h whole cube into MEC square. What about U0? Well, U0 equal to 8 pi by 3 again MEC divided by h whole cube, the same thing but MP multiplied. So this is what we have. Now I am going to write down the result of these integrations. I am not going to do them, but I am going to write down the results and then we will discuss afterwards. So for pressure first. Now you see, we can write the pressure as Pe equal to pi me to the power 4 c to the power 5 divided by thrice of h cube into fx. Okay, and this is approximately equal to, if we write down the numbers, then it is equal to 6 into 10 to the power 22 fx, and the unit is dyne per centimeter square. So you must be wondering about fx. What is fx? Well, fx is basically a function, just a second, fx is a function which is given by x twice x square minus 3 into, using basic integration. You can also check this, it is not very hard, I assure you, plus in class 12 or even in graduation you have done similar integrations. X plus 1 plus x square to the power half. So this is the entire form of fx. Now it is important to note that this fx, you see, if we write this, if we expand this, then you will see that this fx can be written as 8 by 5 x to the power 5 minus 4 by 7 x to the power 7 plus. So you must be thinking, sir, what expansion? So what I am going to do is, I am going to expand this fx for two cases. One, x tending to 0, another x tending to infinity. And both of these are very important. One corresponds to the non-relativistic case, another corresponds to the ultra-relativistic case. Okay, so this is what I am doing. Again, I ask you to check this. First, this integration itself. Second, how we are getting these forms. So let me write it down. So plus 1 by 3 x to the power 9 minus 5 by, it will be 22 x to the power 11, and so on and so forth. Now this limit is for x tending to 0. Similarly, we can again have another limit which is twice x to the power 4 minus thrice x square plus so on and so forth, and this limit is for x tending to infinity. Okay, so this is it. Again, let me write down the case for kinetic energy density. Energy density. So you see, we can write down the kinetic energy density as UE is equal to, just similar to the previous case, of 5 divided by thrice of h cube, and instead of fx we will have gx here, where gx is equal to 8x cube 1 plus x square to the power half minus 1, and this time we have got fx as well. So this is the expression for gx. Now let me write down the two forms for gx. So we have, you see, gx is of the order of 12 by 5 x to the power 5 minus 3 by 7 x to the power 7 plus 1 by 6 x to the power 9. In the next class, I would like you to show me that this is indeed so. At least do this expansion, because why I am writing this? I am basically giving you a sort of homework to really check that this is happening. And in fact, you can expect such a thing for your examinations as well. So I can ask you that, starting from this expression, do the two calculate the two limits of x and then discuss the consequences, what happens afterwards. Okay, so this is important. Don't just take these expressions for granted. Okay, x to the power 11, and this is the limit for x tending to 0. The next one is for x tending to infinity, and here you will get 8x cube plus 7x square minus so on and so forth for x tending to infinity. Okay, so basically you see we started from here, and then we did the calculations, and I am not showing you the entire stuff. It is expected that you will do this yourself, and then I am talking about the two very important limits. Okay, here. Now let's see. So let me first talk about the two. So we will now talk about the two limits. Okay, so you see the first limit is xf much less than 1, or basically xf tending to 0, right? What does this mean? This means that the gas is degenerate and non-relativistic. What about the other case, which means xf is much greater than 1, basically xf tending to infinity. So this means again the gas is degenerate and ultra relativistic. So these are the two limits. Okay, now in case of, so for the non-relativistic case, you see, for the non-relativistic case we have basically Pf is much less than MEC, or EF is much less than MEC square, and as a result we have XF is much less than 1. So this is the reason. And here in the previous expansion, this case here, so we will be picking for x tending to 0, in this limit we will be picking only this term. So in this case we will have fx is of the order of 8 by 5 x to the power 5 only. Okay, similarly you can also check this from this case here. So what is happening alternatively, you can say that when x is much less than 1, then we have basically this thing here. So you will see, let me write down, this is quite simple, or alternatively, so from that expressions we can write 1 plus x square is approximately equal to 1, and as a result of this I am now writing down the entire expression. So already we are having this relationship, rho is equal to rho 0 mu e xf cube. This doesn't change. The other one, P E non-relativistic, you see this one, it becomes equal to, let me write it down, 1 by 5 u0 xf to the power 5, and again we can write it down as k non-relativistic, some constant, into rho by mu e to the power, you see the power is 5 by 3. What about the energy density E non-relativistic? This one is basically 3 by 10, and what happens for this case is that in this non-relativistic case, similarly we can do the approximation, and there we will have, you see, just like here we are choosing the first term 8 by 5, here we will be choosing the first term of this expression. Where is it? Here, which is 12 by 5 x to the power 5. So 12 by 5 x to the power 5, and upon doing these calculations you will get that the result is this 3 by 10 u, okay, 3 by 10 u0 into xf to the power 5, or this is just equal to 3 by 2 Pe non-relativistic. So this is the case for the non-relativistic case. So this is NR, equation of state, whole forms, rho EPNR U ENR. Okay. Acha. What about this constant? So only one constant is there, K. So let me write down the value, K NR. Its value is 0.99 into 10 to the power 7 joule meter per kg to the power 5 by 3. Okay. Now remember that this is just the pressure and kinetic energy relation as we will expect for any non-relativistic gas. Now let me talk about the other extreme, or the ultra relativistic case. Okay, now here you see we will be approximating fx as the first term of the other expression. Similarly for gx we will be again approximating with the first term for the expansion. Here you see, so for gx this one, and for fx this one. This is what we are doing. Okay, and also you can check alternatively is that in the expression over here, this time in the ultra relativistic case, so basically what is happening this time, xf is much greater than 1. So what we can do is that this expansion we can approximately use this. Okay, so in this integration if we do that, you will see that this is what we will get. I'm just showing you an alternative way of thinking. Okay, so upon doing this we get the result as, again, rho is equal to rho 0 mu e xf cube. What about Pe ultra relativistic? This one you see it becomes 1 by 4 u0 xf to the power 4, which is equal to k ur ultra relativistic constant rho by mu e to the power 4 by 3. Okay, and what about the energy density? Again E ur, so this is equal to, you see, 3 by 4 u0 xf to the power 5, or this is equal to thrice of E ur. So this is the relation for ultra relativistic case. Okay, now this k ur constant, this is equal to 1.23 10 to the power 10 joule meter per kg to the power 4 by 3. Okay, again note that this relation between pressure and energy density is just what we will expect for any non-relativistic gas. Okay, now another very interesting point is the transition. So what about the transition between non-relativistic gas, again degenerate, and ultra relativistic gas, degenerate? And this transition will happen when the Fermi momentum, right, Pf, is about equal to MEC, which means xf is equal to 1. And so let me write down. So this means let me write it down. So basically we can write using this expression equation 75. So here this condition becomes rho is equal to rho 0 mu e, which is just equal to 0.98 into 10 to the power 9 mu e kg per meter cube. So at this density we will have, you can say, from non-relativistic to ultra-relativistic transition going on. Okay. So you can say, well, in this transition region we can remember, we can either use the exact parametric formula or use the following approximation. So in this transition region we can use something like this. So degenerate, so it will be approximate relation PE NR to the power minus 2 plus P E UR. Okay, so this is the approximate relation that we will be doing. So now it is important to note that this is an interpolation, right? Now this interpolation chooses the smaller of the two limiting case formulas, and important to note that this is accurate to about 2%. Okay, so we have talked about this very important case, right? Any questions till now? Now let me little bit talk about the finite temperature electron gas, or basically T not equal to 0 case. In very brief, this will be a brief discussion. The full discussion I will talk about in a separate lecture. Now we already know two equations of state for finite temperature electron for non-relativistic electron gas, right? We know two equations of states. The first one is when the gas is non-relativistic and when the gas is non-relativistic and non-degenerate. Now this occurs when the gas density is low and temperature is high. So this happens when you see density is low and temperature is high. Or more precisely, this happens when MEC square is much greater than E minus mu, much greater than kBT. And the electrons here behave as classical gas. And what they follow is basically the Maxwell distribution. So non-degenerate case, and we have this relation. We have discussed about this previously. Okay, equation 86. Let me check if I have done the nomenclatures of equations correctly. Okay, this should be equation 85. Let me check this. This should be equation 85, right? And this one here, rho value, this should be equation 84. Okay, going to previous lecture. These three correspondingly for the ultra relativistic case, they will be equation 83. Okay, again these three, they will correspond to equation 82 together. And then coming back, okay, yes, 81. Okay, fine. So we have checked our nomenclature of equations. Okay, no problem. So we are currently with equation 86. Okay, fine. Now what is the other case that we have discussed? Well, you see, the second case is when the electrons are degenerate and gas can be regarded as cold. So this means that temperature is much less than critical temperature, right? In this case, the equation of state can be well approximated by our T is equal to 0 completely degenerate gas, right? Completely degenerate gas, basically equation 85, which means just the previous case here, this one. Now the difficulty arises when we have non-relativistic and partially degenerate regime. So problems arise for non-relativistic and partially degenerate regime. That means, so this means when E minus mu is of the order of kBt, okay, and for that there is no analytical expression, but we can sort of use the following approximate formula similar to the previous case, and again this is correct. So this is problems, and this is again correct to up 2%. Okay, so what is the formula? The formula is like this. So E to the power half, equation 87. Of course, this is given by equation 85. Now, this last formula, you see, it selects the larger of the two limiting formulas, two limiting pressures. Again, similar to the previous case, let us talk about the transition. Okay, so let us now try to find the region in the density temperature plane, rho T plane, where there is a transition from the non-degenerate to degenerate electron non-relativistic gas. Again, non-degenerate to degenerate electron relativistic gas. Now this can be obtained by, you see, this relation. If you do this equality, or basically ENR, and this gives us this following relation. Let me write it down here. So this is the relation approximate, and this gives us this temperature mu E or temperature density relation. What it looks like I will talk about later on in the density temperature plot. Okay, so this is equation 88. Okay, now let me talk about the electrons in the sun and a very important concept of helium flash. Okay. Okay. So just let me show you the, so this is what we have been talking about. So we have talked about the transition. This transition we have talked about. We have calculated this transition over here, right? This constant density line, remember? And just now we have also talked about this transition over here. So these two transitions. The other cases we will talk about later on. Okay, now when kT is much greater than MEC square, then photon-photon collisions produce electron and positron pairs, right? And there will be modifications as well because of this. We will talk about these things later on in the lectures. Let us go slowly right now. So as I was talking about, we will talk about electrons in sun and helium flash. Okay, now we have already seen that in our previous lecture that at the center of the sun the gas can be approximated as an ideal gas. Right, in the previous class we did the calculations for that. So gas at center of sun we can approximate as ideal gas. Good. Now as the sun evolves, so as sun evolves, what happens? The central hydrogen will fuse into helium, right? And eventually a central helium core will form. So we will have later on a helium core where there is no longer hydrogen available for nuclear burning. Afterwards, the heat that leaks out as radiation cannot be replenished by hydrogen fusion reactions. So the core contracts as it loses energy. The temperature, what will happen to it? Of course it will rise due to the work done by gravity compression, right? Now the temperature of the hydrogen shell surrounding the helium core will also rise. So eventually the temperature of the hydrogen shell is high enough to burn hydrogen. The energy generated in the shell is much higher than that generated by core hydrogen burning along the main sequence. Now, not all the large nuclear energy can be radiated. In fact, part of the energy is used to push the envelope outward, and as a result, the star will become hundreds of times larger than the present day sun. And in other words, you can say that the sun will enter the red giant phase in the HR diagram. This is an important phase. Now, through this phase, eventually the core of the sun will reach a temperature. So the core will reach a temperature of the order of 10 to the power 8 Kelvin. And again a number density of electrons of the order of 3 into 10 to the power 34 per meter cube. Now let us see again, similar to this calculation, let us see whether the electrons are degenerate in this case. So let me do the calculation, just a second. Okay, so let us do this calculation. So the critical number density, again NQ, it is equal to twice pi ME kBT by A square whole to the power 3 by 2, and this time comes out to be 2 into 10 to the power 33 per meter cube. Now you see the actual physical number density is higher than the critical number density. Therefore, what you can say? So you can say the electrons are highly degenerate. So this time we can say that the electrons are highly degenerate. Okay. So this is NQ, right? And previously I talked about the NE. So NE is 10 to the power 34 and NQ is how much? 10 to the power 33. So this means that the physical number density is higher than the critical number density, much more higher. So this means that the electrons are highly degenerate in helium core. Now although the temperature of the electrons is low, by the requirement of degeneracy, it is high enough to eventually initiate the helium fusion in the core, which is basically, so helium fusion, I'll talk about the details later on. So basically we will have 3 alpha forming 12 carbon reaction, and this triggers a very violent event known as helium flash. It is a very violent event. Now what happens is that in normal materials, you see, when the temperature increases, the pressure increases. You see, in normal materials, as temperature increases, so pressure also increases, and it expands and pushes the surrounding material or surrounding gas outward, right? So as the temperature drops, as it loses energy, such systems, so this is basically the attribute of thermally stable systems. Okay, however, what happens this time because of helium burning is that, however, as the helium burning, so as helium burning occurs in degenerate core, the system is thermally unstable. Now why and how? Both of you must be thinking, how can you say that the system becomes unstable? Now this can be seen, you see, the energy generation rate, you see, is extremely sensitive for temperature. In fact, this energy generation rate epsilon is of the order of, you see, this is a relation for helium burning, T to the power 40. So what does this mean? Temperature to the power 40. This means that, say for example, if the temperature rises by 10%, then the energy generation, so if T rises by 10%, then this energy generation rate epsilon increases by a factor of how much? You can 45. So it increases by a factor of 45. So you see, when the helium burning reaction starts, the energy liberated increases the temperature locally. But because of the degeneracy, the rising temperature does not increase the pressure. The latter means that the core cannot expand and cool itself. And this is where the instability occurs. So what happens is that the increasing temperature means the reaction 3 alpha to 12 carbon runs faster. So higher temperature means higher reaction rate. So this reaction runs faster, and so on. And we can have a thermal runaway. And as a result, the luminosity can increase by a huge factor, and you'll be amazed to know that all this happens in a few minutes. Such fast rate. Eventually, the core degeneracy is lifted by expansion, and the star becomes thermally stable again. Because this flash, this sudden release of energy in just few minutes happens, so we can say that this is sort of huge flash, energy flash. And as this flash happens so fast, it is not easy to follow the evolution even with a large modern computer. In fact, the details of how the degeneracy is lifted are still not completely understood. Okay, so you see, there is a lot of scope for you youngsters. You can contribute a lot in this field. Now, the sun does not have sufficient mass to go beyond helium burning. So what will happen is that it will end with the sun, it will end becoming the CO white dwarf, carbon oxygen white dwarf, where the electron degeneracy is very important. And we will discuss about these cases when we discuss about white dwarfs later on. Okay, so after this, now let me talk about the next very small part. This is but also important. So let us talk about the electrons in massive stars. Now let us consider the importance of degeneracy as a function of stellar mass. You see, we have already shown previously that Tc can be written as this P by R. So this means that this is basically proportional to m to the power 2 by 3 rho to the power half, 1/3, where we have used R proportional to m to the power 1 by 3 rho to the power minus 1 by 3. Now you see, since the central temperature of nuclear burning is fairly insensitive to the mass, this means that the central density at given Tc is lower for more massive stars. The degeneracy in massive stars is therefore less important. In fact, for stars with mass greater than 10 solar masses, the degeneracy of electrons is never important. In most stages of stellar evolution. And for stars with of the order of twice solar mass greater, the helium ignition is relatively peaceful. So this means that no helium flash occurs. Okay. However, at their end stage of evolution, they explode as supernova. So you can say that flash doesn't happen at that time, but later on during supernova, there is a huge, even more large release of energy. And for this stage, the degeneracy of electrons again play a crucial role. And we will discuss about this later on in our course.